Good afternoon. I shall present the research myself and colleagues have produced at WSP on providing a data-driven multi-objective design tool called DAISY for a real-world application. Today's presentation will delve into an overview of our work and the transition to a performance-driven design methodology, the case study methodology we employed, results and discussion highlighting DAISY's capability in design space exploration, how it can challenge traditional design preconceptions. Lastly, I will conclude with key takeaways and potential avenues for further research. A shift towards a performance-driven design approach. We have a choice between action and climate disaster. That's it. We must recognize that there are no bystanders in the triple planetary crisis of climate change, nature and biodiversity loss, and pollution and waste. In the construction industry, we all have a significant role to play in the required transformation. This transformation necessitates both a cultural and a technological shift. So what has gone wrong with the industry's current approach? Some argue that we already have all the tools necessary and that achieving low carbon and high sustainability buildings is within reach. They believe that with a bit more effort in making zero carbon buildings more universal and transitioning to renewables, we can achieve our goals. However, we need to gain perspective on sustainability and sustainable design. By turning the dials on sustainability, merely being less bad does not suffice. This work introduces DAISY, a multi-objective optimization parametric design tool incorporating machine learning for designer-led optimization as part of the early stage building design. DAISY engine utilizes rhinoceros and grasshopper modeling tools and custom Python scripts for performance-based parametric design. While Design Space Navigator, or DSN for short, utilizes surrogate models, generative AI, statistical approximations of the nonlinear design space, which enables users to intuitively navigate the design space and generate near real-time predictions of performance objectives. For this study, 3 performance indicators for the multi-objective optimization are building embodied carbon, referred to as carbon, energy use intensity, referred to as energy, and spatial daylight autonomy, referred to as daylight. To help explain this, we used our DAISY engine to optimize each objective in isolation. To the left, optimum daylight results in slender designs with high glazing ratios. In the middle, optimum operational energy or carbon results in compact forms with minimal glazing ratios. On the right, optimum embodied carbon results in low-rise buildings with expansive foundations. Whilst this approach of working as discrete disciplines can yield improvements in the targeted area, it often fails to consider the broader context and potential trade-offs of other design disciplines and their objectives. This is a significant problem impacting the design of buildings today. Balancing design trade-offs can be achieved through multi-objective optimization, or MOO for short, which simultaneously maximizes a set of performance objectives through searching a multi-dimensional design parameter space to identify the Pareto front. Despite advances in parametric design and MOO for buildings, limited work has explored MOO for simultaneous optimization of carbon, energy use, and user comfort metrics such as spatial daylight autonomy and overheating. Performance-driven design tool called DAISY. In this paper, DAISY is applied to a 63-story commercial building design, demonstrating machine learning, surrogate modeling's potential in aiding user-led design exploration and informing clients about design trade-offs. The chosen building, conventionally designed, stands tall in central London, emblematic of modern urban edifices. Our study results remain anonymized, but a design with comparable energy, carbon, and daylight is selected as the benchmark for relative performance. Design space comprises 8 facade variables as shown in orange and 7 shape variables as shown in blue. The presented histograms depict. Solid histograms are samples obtained through the hypercube sampling, showing a uniform coverage. Translucent histograms are samples obtained from the last generation of the genetic algorithm sampling, focusing on the regions of the search space that contain Pareto-optimal solutions. Dashed lines indicate benchmark structure parameters, noting how the glazing ratio is high on all elevations typical of modern tall buildings. DAISY evaluates embodied carbon considering structural and facade elements. Structural carbon is determined using an in-house tool, system ABC, aligned with Eurocode standards. Facade's embodied carbon tool is called FACE. Each facade orientation's carbon is computed using a weighted average of a standard facade bay, adjusted with design space variables. Operational energy is calculated by using a dynamic thermal model in Grasshopper augmented by the Honeybee plugin. implementing simplified mass site context from OpenStreetMap for shading it from nearby structures. Lighting is dynamically controlled based on daylight. Average energy use is computed for the ground, top, and mid-level floor. For each level, energy use is area-weighted per facade orientation. HVAC systems are simulated with specific units such as heat pumps and air-cooled chillers operating as per ASHRAE's efficiency curves. Spatial daylight autonomy indicates the percentage of floor area maintaining illuminance levels above 300 lux for half the occupied duration. Recognized by WELL and LEED certifications, it accounts for local climatic conditions and adjacent structures. Daylight calculations utilize a 2-meter sensor grid at 1.2 meter height. Perimeter core metrics are adjusted and internal partitions omitted, showing accurate daylight measurements within the central core. Challenging preconceptions and discovering the unknown. Comparative performance indicators from DAISY engines showcase the genetic algorithm, or GA, optimization in orange, hypercube sampling in blue, and the benchmark structure data. While 2D subplots present Pareto fronts for individual performance indicators, the 3D subplot combines genetic algorithm and hypercube data for the global perspective. The data reveals superior solution space mapping through genetic algorithm whilst maintaining diversity within the design parameters. Relative to other designs, the benchmark structure has a high external window area and a low form factor as shown on the left. While the benchmark structure is Pareto efficient, as shown on the right, with daylight higher than 72% of designs simulated and a carbon lower than 60% of designs simulated, the benchmark structure's energy is higher than 94% of other designs. Plotting the normalized performance indicators relative to the gross internal area, GIA, the results highlight that, as shown on the left, a building that maximizes GIA reduces carbon by needing less carbon-intensive facade. But this limits its potential for maximum daylight, as shown on the right. This relationship stems from exploring designs with a fixed number of stories, focusing on the impact of form, factor, and shape on tall buildings. As shown on the right, to achieve a high daylight, the GIA must be smaller. However, as the GIA decreases, other design parameters must be holistically selected to avoid an increased energy arising from higher peak cooling and heating requirements due to factors such as high glazing ratio or aspect ratios. This is shown by a large range of possible energy intensities for a low GIA, as shown in the middle plot. Such insights underscore the intricate interplay of building design disciplines. Reliance on traditional, intuition-based methods may not be adequate to advance modern designs. Therefore, there's an emerging need for a performance-driven approach. Machine learning using discriminative models such as random forests are used to identify roadmaps for improving global design efficiency, identifying predictive variables for specific design performance, and enabling informed navigation of the design space. Random forests are particularly useful for ranking variable importance, which capture nonlinear relationships through the binary splitting process in decision trees. 3 design scenarios relative to the benchmark based on real-world needs of the designers are examined. Firstly, characterizing designs with daylight below 40%, the limit of good daylight as defined in the LEED standard, as shown by black. Routes to reduce energy of the benchmark structure through increasing daylight and carbon, as shown in green. And lastly, routes to reduce energy of the benchmark structure through decreasing carbon and daylight adhering to standards like WELL and LEED, as shown by the purple and orange respectively. Starting with the first scenario, a random forest identifies the external wall area as the greatest predictor for daylight below 40%. This is followed by the minimum radius of the design and a range of other parameters with a smaller importance. Counterintuitively, the average window-to-wall ratio of buildings is a relatively poor predictor of designs with daylight below 40%, as it fails to account for the combined effect of the building's form and internal floor area. For the second scenario, as shown by the movement into the green design space, increasing daylight of the design allows for reduction in lighting and heating, potentially reducing the energy of the design. However, due to the high carbon of the facade, there is a strong positive correlation between daylight and carbon. The simulations demonstrate that increasing daylight can allow reduction in energy of the benchmark of up to 7.1%, moving the energy from higher than 94% of the other simulated designs to lower than 98% as shown in green. However, through accepting smaller reductions in energy, more palatable increases in carbon can be identified. Partial design space catalogues, as shown below, are useful to visually explore the buildings that belong to particular zones in the design space. Relative to the benchmark structure, designs which reduce energy through increases in daylight and carbon tend to be relatively slender buildings with high form factors enabling high daylight trade-off with energy. However, despite the increase in carbon correlating with increase in daylight relative to the benchmark, a reasonable compromise can be made such that the lowest carbon building has an energy lower than 70% of the other designs simulated, enabling a reduction in energy of 3.7%, but requires an increase in carbon of only 2.7%. Using random forest models to assess the dominant design parameters to reduce energy through increased daylight emphasize higher external wall areas, lower minimum radii, lower window-to-wall ratios given the benchmark building already has its maximum window-to-wall ratio. When moving towards more slender buildings with a greater external facade area, the window-to-wall ratio needs to reduce, and high surface area to volume ratios, which relates to the strong predictors of low radii combined with high external wall area. Overall, these complex trade-offs between features predominantly mitigating heating and lighting requirements. For the final scenario as shown by the movement into the orange and purple design space, decreasing daylight improves the energy efficiency of the facade and decreases the cooling requirements for the building, enabling a lower energy. In the context of carbon-neutral buildings, this has the added advantage that, due to the strong correlation between daylight and carbon, reducing the daylight reduces the carbon. While adhering to LEED standards for daylight, the limitation is that a maximum energy reduction of 4.4% is attainable. As with the previous partial design catalogue, there are a range of designs which can enable reduced energy through decreased daylight. These designs tend to be relatively bulkier, with low form factors enabling reduced facade area, reducing overall carbon, also allowing daylight to trade off with energy. Using random forest models to assess the dominant design parameters, 3 features dominate which enable a reduction in energy, carbon, and daylight relative to the benchmark: lower external window area, lower form factor, and higher external wall area. Designs achieving lower energy through diminished daylight present a larger external wall area. This relationship stems from the interaction with other key parameters, leading to bulkier structures with lower average to wall window ratios. These designs land within the energy's local optima, balancing lighting, cooling, and heating needs. In addition to random forests, quantile regression models are used with the key advantage over linear regression is that quantile regression does not require symmetrically distributed outputs and it is robust to outliers. The plots show the fitted regression coefficients for the scaled inputs and output features. The relative magnitude of these coefficients give an indication of the relative importance of the input features. Keynotes on the model's coefficients for the performance objectives emphasize, for energy use intensity, as might be expected, energy is dominated by positive correlations with the window-to-wall ratio and the external wall area. These 2 variables are known to affect the heating, cooling, and lighting of the structure. For daylight, as might be expected again, the daylight is predominantly dominated by a positive correlation with the average window-to-wall ratio, with a modest positive correlation with the south glazing ratio. In the world of architecture, intuition is often a silent guide. However, DAISY transforms this tacit knowledge into an empirical, data-driven model. The use of random forests and quantile regression as discriminative models is pivotal here, offering insights into variable importance and their interrelationships. Moreover, the introduction of generative pre-trained transformers, GPT models, as a conversational co-pilot elevates its experience. These models provide real-time, contextually aware insights and recommendations, effectively transforming data into actionable intelligence. With DAISY AI, building design intuition is not just about leveraging years of experience, but augmenting that wisdom with the precision, speed, and intelligence of AI. Key contributions and further work. The results presented in this paper highlight how computational exploration can meaningfully drive carbon efficiency in high-performance engineering designs. It has also shown the importance of early-stage design and the form-generating potential both structural and energy models can have in high-performance designs. Despite advances in parametric design and MU for building structures offering valuable insights in global trends and design parameters, its practical application can sometimes be limited. This is especially evident when local minima suggests that achieving optimal designs may require counterintuitive decisions. Such scenarios underscore not only the limitations of traditional design approaches that can lean heavily on tacit knowledge, but also large-scale sensitivity analyses that miss the local optima. Lastly, these same design tenets can be applied to other engineering projects using the performance-driven framework demonstrated in this paper. The modification of design transfer formulation, The same calculation engine can be applied in areas of diverse as site master planning, utility routing and sizing, or the design of individual units within a broader building. The case study results have highlighted how DAISY enables a generation of high-performance building designs that maximize spatial daylight autonomy whilst minimizing energy use intensity and building embodied carbon. Beyond this, surrogate modeling in the form of random forests, implemented as part of the DAISY Design Space Navigator, allow designer-led optimization by quantifying relative feature importance, enabling informed navigation of the design space. Two roadmaps for reducing energy of the benchmark building were identified. Firstly, through increasing the daylight and carbon by predominantly mitigating heating and lighting requirements, and secondly, by decreasing the daylight and carbon by striking a balance within the energy's local optima, balancing lighting, cooling, and heating needs. Quantifying these design trade-offs through multi-objective optimization allows for user-informed, data-driven decision-making, which is crucial in the move to a net-zero built environment. The case study presented here represents an initial verification of the performance of DAISY and the feasibility of data-driven modeling with Mu to enable high-performance building designs as part of the early-stage design process. Future work will continue to refine DAISY to reflect the needs of the client and the design team, including additional objectives like overheating and broad application to master planning. Some of the technologies we are developing include distributed computing, surrogate modeling to allow real-time approximated simulation design, and generative AI, particularly retrieval augmented generation, for enhanced data insights. Thank you for your attention.